Okay, today's talk is Brian Cox makes a mistake about relativity, question mark. The main site I will be referring to is called Why Professor Brian Cox Was Wrong, and it's at this website address here. The person thinks Professor Brian Cox made a mistake about Einstein's relativity, and the answer is he didn't really, but it illustrates the confusion that Einstein has got us into with words and how loose talk can misrepresent things. So we'll go to the video now. Here we go. If Brian Cox. Go.
You can see then why actually moving clocks run slowly.
I'm going to also ask you to watch your...
So that was very quick, so if we can try to do it again. Here we go.
You can see then why actually moving clocks run slowly.
Right.
I'm going to also...
And that's the bit which the person thinks Brian Cox has got wrong. Let's see. The person who's giving this talk here is... Where's it gone? This person here, that's Richard Wolfson. If I can enlarge it a bit more. It's him. This person, Richard Wolfson, he's a professor of physics. He's given a talk about relativity, and a person thinks Brian Cox has made a mistake, and he's quoting this person as having shown on Brian Cox to be wrong. If we enlarge it, it gives a talk, and it happens at 1739, the relevant part. Let's see, there. So pick it up from here, from the talk given by this person. Here we go.
What it really says. It doesn't say moving...
Right, that didn't come off very well. Let's go again. Time delay.
Here's what it really says. It doesn't say moving clocks run slow. Instead it says something a little more complicated. It says if I have two events and I measure the time between them on a clock that is present at both events. Remember the light clock when it was in the frame of reference where it was at rest. That light clock, that same box was present at the emission and the return of the light flash. Okay, we're going to now replace that light box with a couple of real clocks. Okay? And so what does it say? It says something like this. It says, first of all, we're not going to say moving clocks run slow anymore. That's bad, relativistically incorrect. We're going to say a little more sophisticatedly, the time between two events is shorter when you measure it with one single clock.
Right, so this is the point from this Professor Wolfson that's saying moving clocks run slow is a bad thing to say, and it's not relativistically correct to say that. It's kind of like political correct wording. Just to say moving clocks run slow is a bad way of talking about it, and so it's wrong to say that. And it's what Professor Brian Cox is saying here. Let's get yeah, it goes by very quickly.
You can see then why actually moving clocks run slowly.
So Brian Cox is saying moving clocks run slowly, and this Professor Wolfson is saying that's a bad thing to say. So the person who's put this video on the internet is thinking Brian Cox got it wrong. Let's see what he says. He's saying here, a plea to Brian Cox and relativity teachers everywhere. In my frame of reference, the Stanford linear accelerator is 2 miles long. In the electron's frame of reference, the accelerator is 3 feet long, and that's just the way it is. Neither of us are wrong, neither the electrons nor I. So let's avoid putting a specialness on a particular frame of reference. Uniform motion is motion in a straight line at constant speed, motion that is not changing the general theory relativity deals with accelerated motion. And he's saying, I'll create this video, but really he's not really dealing with that. He's picking up on Brian Cox saying moving clocks run slow.
You can see then why actually moving clocks run slowly.
He's saying, he's really picking up that Brian Cox shouldn't really talk in that way about things, which I think is a bit nitpicking. Let's see. And so somebody here makes a comment, language important, the way we think about things is affected by the words you use to describe them. So it's quibbling over the way Brian Cox talked about things. It's he should have said something like moving clocks, if you were in a frame of reference and you're seeing a clock moving, then relative to you in the context of special relativity that clock will be slow. But he didn't really get into saying something is more precise or complicated like that. He just made a general statement of,
you can see then why actually moving clocks run slowly.
Moving clocks run slowly, and it's just a quick abbreviation of a more complicated explanation of what's going on. So it's really just loose talk, and that's really the comment on that. If I bring back up the note, so the question is, Brian Cox makes a mistake about relativity, and really it's just he's probably getting a bit tired of saying the same thing over and over again, and he's just said moving clocks run slow, and this other person, Professor Wolfson, thinks you've got to be more precise in talking about things. So really it's just a question of loose talk, and this is the sort of, like, when you look into it more, it's a problem of getting precise communication of what Einstein is saying. He sort of like really has messed up the words on things, and I think so if we go into this person's talk, I will now pick up things I'm going to disagree with. So this is about a 20-minute talk before getting to the bit where he tells you that moving clocks run slow is a bad way of talking about it. So I'm now going to criticise Professor Wolfson's talk. He's going to talk about relativity, and I'm going to criticise it.
I'm going to also ask you to watch your language. And this is a plea not only to you in my audience, but also to some of my fellow teachers of relativity, because it's very easy to make statements that violate the spirit of the relativity principle.
So that's the sort of criticism he's raising, and if you go back to Brian Cox again,
you can see then why actually moving clocks run slowly.
So that sort of criticism is, so say, applying to Brian Cox. You've got to be very careful with your wording when you're talking about relativity, and it is quite a problem. So picking up again.
I'm going to also ask you to watch your language. And this is a plea not only to you in my audience, but also to some of my fellow teachers of relativity, because it's very easy to make statements that violate the spirit of the relativity principle. You've heard about
Right, so you've got to be careful with using your language, and it's Einstein has made this confusion, in my view, and also when you look at Einstein, it's rubbish anyway, nonsense. So not only have you got problems with talking about Einstein's relativity, you've got problems in talking about nonsense. So let's get into it.
Statements that violate the spirit of the relativity principle. You've heard about political correctness on our campuses. You have to make statements that are in tune with the prevailing political norm.
There you go, political correctness. So you've got this problem now with political correctness, and presumably you've got this problem of talking about special relativity and general relativity in a way which is sort of equivalent to being politically correct.
our campuses, you have to make statements that are in tune with the prevailing political norms. Well, I don't want to get into that. But I do want to ask you, and ask myself, and ask my fellow teachers of relativity to be relativistically correct in our language. And what that means is, when you're describing what happens to space and time, be very careful to avoid any statements that might suggest there is a preferred frame of reference, a preferred state of motion. Why? Because there isn't a preferred frame of reference, and there isn't a preferred state of motion. The Copernican principle has been expanded through special relativity to say that all...
So he's saying there's no preferred frame of reference, and I think he's talking absolute rubbish there. But the problem is the word preferred can mean several different things. If we call it up here, I got it from Wikipedia. Preferred frame. In theoretical physics, a preferred or privileged frame is usually a special hypothetical frame of reference in which the laws of physics might appear to be identically different, simpler from those in other frames. In theories that apply the principle of relativity to inertial motion, physics is the same in all inertial frames, and it is even the same in all frames under the general principle of relativity. This is Wikipedia, and I don't really agree with this too much, because it's stating a belief in Einstein's relativity, and Wikipedia does go under lots of amendments and revisions, but you get the basic idea that this is what he's talking about as a preferred frame. So back to here, so we pick it up again. He's saying there's no preferred frame in Einstein's relativity. I think he's dealing with special relativity, and
careful to avoid any statements that might suggest there is a preferred frame of reference, a preferred...
So he doesn't want people to make statements which suggest there's a preferred frame. So you could talk about special relativity and so forth, and it would be implied from the way you're talking about it that what you're talking about is having a preferred frame, and he doesn't want you to talk that way. And it's more than nonsense, it's more playing around with words. It's what's come from Einstein.
In time, be very careful to avoid any statements that might suggest there is a preferred frame of reference, a preferred state of motion. Why? Because there isn't a preferred frame of reference, and there isn't a preferred state of motion. The Copernican principle has been expanded through special relativity to...
So I think all that is a bit of nonsense. It's the word preferred. It's really to do with semantics a bit about what does the word preferred mean. But so we'll let him carry on for a bit, and then
say that all uniformly moving frames of reference are equally valid places, situations to do physics. So avoid any statements that would suggest anything to the contrary. For example, in the last lecture when we put you in first the car, then the airplane, and then the spaceship, and we said, well, we...
Unfortunately, don't have the last lecture, but you get the general idea. Hopefully you know about that sort of thing, that when you're dealing with inertial frames of reference, then you're treating all those inertial frames as being much the same, and physics as being the same in each of those frames. Right.
In the last lecture when we put you in first the car, then the airplane, and then the spaceship, and we said, well, we both measure the same speed for light. We said, how could that possibly be?
Right, so you're in all these inertial frames, you are, so say, measuring the same speed of light, and as I pointed out in one of my talks, where is it? The lie on which Einstein's relativity is built. So in this, I explain that is basically a lie. You didn't really get that from experiment. If you are assuming the speed of light as constant in a vacuum, free of influence of fields, and for inertial frames and so forth, they were not able actually to get that from experiment, and so that sort of theory had failed, but they are falsely stating that theory. Okay, so we can go back to him again. So that's one point, but now we're getting on to the confusion of preferred frames.
And I simply hinted at the end of the lecture that it must mean that something is different about our measures of space and time. You might jump to the conclusion that, well, maybe the meter stick in the moving vehicle shrinks. Maybe something funny happens to the clock in the moving vehicle.
Yeah, so by that law of relativity about the speed of light, they then have to mess up the measurements of length and measurements of time. So that's a consequence of that particular type of lie.
Vehicle shrinks. Maybe something funny happens to the clock in the moving vehicle because the vehicle is moving. That's sort of the philosophy that Lorentz and Fitzgerald had when they suggested maybe the apparatus, the Michelson-Morley apparatus, contracts in the direction of motion. It's really this long, but because it's moving, it got contracted. What's wrong with a statement like that? What's wrong with a statement like that is the sense that somebody is moving and somebody isn't.
So he doesn't want the idea of somebody moving and somebody not moving. So I think he's going to get his knickers into a twist upon that issue, which we'll get to. But it's all this confusion already about the speed of light, and it's just piling on the confusion a bit here.
What's wrong with a statement like that is the sense that somebody is moving and somebody isn't. Moving and somebody isn't. Somebody, probably you think the person on Earth, has the right to assert that they're at rest and funny things are happening to clocks and meter sticks and space and time for the people who are moving. Nonsense. You in the moving spacecraft, moving relative to me that is, you in the airplane moving past me at 600 miles an hour, you in the car moving past me at 70 miles an hour, because those motions are uniform, you have every bit as much right to claim that you're a place for doing physics. You have no more right to claim you're the right place than I do. We both have equal claim on doing physics and doing physics correctly. That's what the principle of relativity says. So don't think funny things happen to clocks.
So, unfortunately, he's getting on to funny things about clocks, but that bit about discarding the preferred frame, so like when you've got a planet, really the planet is rotating on its axis, it's moving around the sun, there is motion going on, and it's not inertial motion. So if you're considering an astronaut leaving the Earth, and you want to consider it in the context of special relativity where you're only dealing with inertial frames, then as an approximation you've got to treat the Earth as being an inertial frame when it's not really an inertial frame. And the rocket you've got to consider as having constant velocity, and then it's an inertial frame. So you have, in the artificial context of special relativity where you've got two inertial frames, and maybe you're treating the Earth as approximately an inertial frame, idealising it to an inertial frame, you're then saying, oh, he's trying to tell you there is no preferred frame. Now the problem with that is, if you're on Earth, you are saying, well, I prefer to make my measurements from this frame of the Earth, and so that's what you want to do. So for you on the Earth, that is your preferred frame for making measurements. And if you're on the spaceship, you might say to yourself, I prefer to make measurements from this frame. So yes, there would be no preferred frame, but because both people want different preferred frames. But what could happen is the person on the Earth and the astronaut decide, we want to keep the Earth as a preferred frame, and we want to make all measurements with respect to the Earth. So the person on the Earth is treating measurements from the Earth frame, and the astronaut's going away and he's still treating his measurements as from the frame of the Earth. So they've both agreed to a preferred frame, namely that of the Earth. in that particular instance. They could have decided on some other frame, so the astronaut could have gone away in his spaceship, and both of them decided, well, we do all our measurements from the frame of the spaceship, and that would be, we'll treat that as our preferred frame. So you've got this ambiguity over the use of the word preferred. People can agree to use one particular frame for their measurements, and so in that context it's a preferred frame. So that is ambiguity from the word preferred. So if we pick it up again, more confusion is going to come along.
The right place than I do, we both have equal claims on doing physics and doing physics correctly. That's what the principle of relativity says. So don't think funny things happen to clocks and meter sticks or space and time because things move. The phrase "because things move" is a relativistically incorrect phrase.
So really, you when you're talking about things moving, you need to say with respect to what frame. And in the case of treating the Earth as your preferred frame, you could say you're treating everything as moving with respect to the Earth. So there you go. It's just really a question of making it clear what you're talking movement with respect to.
Things move. The phrase "because things move" is a relativistically incorrect phrase. You're allowed to say, "I am moving relative to you," or "that clock is moving relative to this clock."
Exactly. You can talk about things moving relative to something, and that's where you can get the idea of frames of reference.
Correct phrase. You're allowed to say, "I am moving relative to you," or "that clock is moving relative to this clock that I'm looking at." But you're not allowed to say, "that clock is moving and this one isn't, and therefore..."
So when Brian Cox was saying moving clocks run slow, really he should have said something more accurate, like a clock relative to me that's moving will run slower according to special relativity. So it was a question of just loose talk by Professor Brian Cox.
Clock that I'm looking at. But you're not allowed to say, "that clock is moving and this one isn't, and therefore funny things happen to that clock." That violates directly the spirit of the principle of relativity, which says all uniformly moving frames of reference are equally good places to do physics. And that means any uniformly moving clock keeps time just as well as any other uniformly moving clock. It's just as accurate. Clocks don't become inaccurate, quote, because they move. Because no uniformly moving clock has the right to say, "I'm at rest and all the other ones are moving." What may be the case...
So no clock has the right to say, I'm at rest and the other ones are moving, but that is true, probably. But what you really got to say is, when the people who are the observers are making their measurements, they can choose to have a certain frame as their preferred frame for measurements. So they could have a certain clock and they say, we prefer to consider that clock as having been put in the preferred frame, and all the other clocks have to take in with respect to that preferred frame. And his use of the word preferred is not really conforming to that way of talking about things, hence it's leading to a bit more confusion.
Uniformly moving clock has the right to say, "I'm at rest and all the other ones are moving." What may be the case, and in fact is the case, is that different clocks moving relative to each other keep different time. But there's not one of them that can say, "I keep the right time and all the rest of you are wrong because you're, quote, moving." Because no... If
you got a preferred, if you decided to agree on a preferred frame, then the clock in the preferred frame is the one where you can decide is going to be the correct time. So as we are Earth-based creatures, what we normally do is we treat clocks on the Earth as being in the preferred frame. So a clock which is not on an Earth-based frame, and say it's in a spaceship moving away from us, is not within the Earth-centered frame, our preferred frame, and so it's going at a different time to one on Earth. So that's one of the confusions they bring into us. But this this problem of the time dilation, as I pointed out, is really being brought about by this lie upon which Einstein's relativity is built. So it's all it's doing is adding more and more confusion by messing up this idea of a preferred frame.
Time. But there's not one of them that can say, I keep the right time and all the rest of you are wrong because you're, quote, moving. Because nobody has the right to say, I am moving. I will even slip occasionally and use phrases that are not correct. If I ever...
So he's prepared to slip occasionally and say things which are wrong. And so this is one of the problems with these people who believe in Einstein's relativity. Even in the context of their belief about Einstein's relativity, they're going to say things wrong. And he's admitted that he's going to do that, and or has done that in the past. So they make mistakes.
Because nobody has the right to say, I am moving. I will even slip occasionally and use phrases that are not correct. If I ever say the moving clock or this is moving, what I really mean is this is moving relative to that. That's why it's a relativity theory. It says only relative motion matters. Lecture 3, we went over this with the Galilean relativity principle. Only relative motion matters. Statements about absolute motion are meaningless. They were in mechanics all along.
I didn't quite get that. Meaningless. Let's get back again.
Matters. Lecture 3, we went over this with the Galilean relativity principle. Only relative motion matters. Statements about absolute motion are meaningless.
So saying about statements of absolute motion are meaningless, and that's also, we've got this problem with the word absolute. If we've decided for our observers to have a preferred frame for which they want to make measurements from, we then call it an absolute frame. So once again, it's a problem with the word being used. There can be agreement between observers just to use one frame of reference, and what word do you use for that? And absolute and the other word privilege can get confused on this issue.
We went over this with the Galilean relativity principle. Only relative motion matters. Statements about absolute motion are meaningless. They were in mechanics all along. They became so in all of physics with Einstein's special relativity.
So it's with Einstein's relativity, it's, I say, getting confused over those terms.
So everybody who's in uniform motion is in an equally good position to do physics.
Yeah, so uniform motion, which is inertial motion, uniform motion is motion in a straight line at constant speed. Motion that is not changing. In other words, the general theory of relativity deals with accelerated motion. So actually, this is his point of view of Einstein's relativity, and this is where a lot of the Einstein believers start getting into a muddle. Some will accept that about as being special relativity, but they will then consider further and consider accelerated motion within the context of special relativity. They would say that special relativity does that, but they will also then try to apply acceleration to it. And with the general relativity, it seems to be the idea of the equivalence principle, where they're saying acceleration due to gravity is the same as any other sort of acceleration. And so then it's a question of, if you've done acceleration in the context of special relativity, are you then able to deal with gravity in that context or not? So it's utter confusion to quite some extent there. People just start off sometimes from the context of special relativity dealing with constant speed, and then they start differentiating that constant speed. So the differentiation of speed with respect to time gives you acceleration. So they're working from that sort of math within that context. So they wouldn't believe that sort of statement of relativity. And it so muddles up with their general theory of relativity.
So let's now move on and see what actually happens to space and time in special relativity. We'll start with time. We're going to be talking a lot in the next few lectures about events. I just want to tell you what an event is so we make it very clear. An event is something specified by giving both its place and its time. For example, your birth is an event. It occurred at a specific place and it occurred at a specific time. Just to give the place, to say New York City, for example, is not sufficient to specify your birth. Just to give a year, 1960, is not sufficient to specify your birth. New York, 1960, that does it. An event is a place and a time. And events are the key things in relativity. So we're going to talk a lot about events. I'm going to imagine a device which I'll call a light clock. Here's a picture of a light clock, and you audio people have a picture of the light clock in your booklet. The light clock consists of a box, just a simple box. At one end of the box is a light source, and at the other end of the box is a mirror. And we're going to imagine a pulse of light leaves the light source, travels to the mirror, reflects off the mirror, and comes back. And we're going to be interested in the time interval between two events. And those two events are the departure of the light pulse from the light source and the return of the light pulse back to the light source after it's bounced off the mirror. If you will, this device is a clock, and that's the fundamental ticking. Tick, as the light goes up, tock, as it comes back. There's one period of the clock, and it keeps doing that. But we're just going to focus on...
So actually we can really put aside the confusion of the preferred frame and the absolute frame for the moment. And we're looking into this light bouncing up and down.
Goes up, tock, as it comes back. There's one period of the clock, and it keeps doing that. But we're just going to focus on one tick-tock of the clock, one outgoing light pulse hitting the mirror, coming back to the light source again. And the two events are light pulse leaves the source, light pulse returns to the source. And we want to know what the time interval is between those two events. So here's our light clock. Now, whenever you see pictures in relativity books or in my course or in anything dealing with relativity, it's crucial to ask yourself, and it's crucial to understand the answer to the question, in what frame of reference is this picture being drawn? Many relativity books fall down, I think, because they fail to tell you that, or sometimes worse, they'll draw pictures that are ambiguous.
Aha! So, what's he now doing? He's now slagging off relativity textbooks. He's saying they're ambiguous. They fall down. So he's not liking other relativity books. So he's trying to impose his version of what he believes Einstein's relativity to be. And when you can pick up a relativity textbook and it might say something different to what this person is saying, and so he's criticising those books that are going to say different to him now. So this is how bad relativity is. He's suddenly trying to change things. It's what you call moving the goalposts. So you've got these books on relativity, and he wants to move the goalposts away from what those books are saying about relativity. He's going to give his own little spin on it.
And it's crucial to understand the answer to the question, in what frame of reference is this picture being drawn? Many relativity books fall down, I think, because they fail to tell you that, or sometimes worse, they'll draw pictures that are ambiguous. They're partly from one frame of reference and partly from another. And in relativity, things tend to look different in different frames of reference.
What? Things tend to look different in different frames of reference. You're supposed to be going by the principle of relativity. So it's one of his little mistakes here. You're supposed to have the same thing from different frames of reference. Or if you are dealing with inertial frames of reference, the laws of physics are supposed to be the same in each frame according to special relativity. So he's fumbling a bit there. He's pointing out textbooks are bad, and he's fumbling.
They're ambiguous. they're partly from one frame of reference and partly from another. And in relativity, things tend to look different in different frames of reference. And it's important to catch that difference. And I'll try to do the best I can. Sometimes I'll slip. But I want to tell you...
It does slip. He's slipping. Slipping already. He's muddling up. We're trying to be accurate on the words being used. He's fumbling already.
That difference. And I'll try to do the best I can. Sometimes I'll slip. But I want to tell you, whenever possible, what frame of reference I'm dealing with. So the picture I'm showing you right now on the left side of the screen is a picture drawn in a frame of reference at rest with respect to the light clock. What that means is we're in a frame of reference, we put this light box or light clock here, and it's at rest with respect to us. That's what I mean by saying this is a picture drawn in a frame of reference in which the light clock is at rest, or equivalently a frame of reference at rest with respect to the light clock. And I'm assuming that I've got a uniformly moving frame of reference. You might say, well, maybe it's at rest. Well, maybe it is at rest, but being at rest is meaningless. Maybe it's at rest on Earth. That's a particular state of uniform motion. Maybe it's at rest.
When you say on Earth, you've got to assume it's an inertial frame. If you've got actual motion of the Earth as it rotates on its axis and so forth. So it's an idealisation to treat the Earth as an inertial frame. So hopefully when they do the experiments they are taking that into account.
You might say, well, maybe it's at rest. Well, maybe it is at rest, but being at rest is meaningless. Maybe it's at rest on Earth. That's a particular state of uniform motion. Maybe it's at rest on Mars. Maybe it's whizzing through space at 99% of the speed of light relative to Earth. But as long as it's moving uniformly, that's an okay frame of reference. So I don't know exactly what the light clock is doing relative to Earth. Doesn't matter. The point is, I'm drawing a picture here from the frame of reference in which the light clock is at rest. And in that frame of reference, here's what's going to happen. The light is going to leave the source. It's going to go up and hit the mirror. It's going to return to the source. That's all that happens. And the light is going to travel a total distance which is twice the length of the box. And that's all we need to know at this point. What's the length of the light path for that light? It leaves the mirror, it leaves the source, it travels up to the mirror, it reflects off the mirror, it comes back and hits the source. And
I think it's worth pointing out that in this setup here, you're only considering constant velocity motion, constant speed motion, and you're not considering any acceleration. So you're not considering anything like a gravity effect on this. So I think that's worth pointing out. So this is just constant. Well, it's a constant speed up, a constant speed back down again.
The source, it travels up to the mirror, it reflects off the mirror, it comes back and hits the source, and we know how far it traveled. It traveled twice the length of the box. No problem. Now, there are certainly plenty of other frames of reference that aren't at rest with respect to the light clock or light box, equivalently through which the light clock is moving. If I'm at rest with respect to the light clock and you go by me at 70 miles an hour in the car, then relative to you, the light clock is in fact moving. In fact, suppose you go by me in that direction, then judged from your frame of reference, the light clock is moving in the other direction, relative to you. And you might say, oh, but it's really at rest. That's not relativistically correct. Both of those frames of reference are equally valid because they're both uniformly moving frames of reference, and no one has the right to claim at rest or not. So is the light box at rest?
Nobody has the right to claim any frame moving and any other frame not moving, unless you can make an agreement on it. You can get observers to agree to treat a certain frame. So this is where the confusion's going. Observers can actually agree a frame to do their measurements from.
Are equally valid because they're both uniformly moving frames of reference, and no one has the right to claim at rest or not. So is the light box at rest, light clock at rest or not? It is in one frame of reference, it isn't in another. And that's just the way it is, and that's okay. So let's look at that second frame of reference and see what happens. So we'll look at the same situation, the light clock, the emission of the light, that's the first event, bounces off the mirror, comes back to the source, that's the second event. We're going to look at that sequence of events, at those two events, in a frame of reference now in which the light clock is moving to the right. That means relative to the frame in which the light clock is at rest, that frame is moving to the left, and therefore the light clock looks like it's moving to the right. It is moving to the right in that frame. By the way, a word to avoid, you might want to say, but isn't it really at rest? Again, avoid the word really in relativity.
That is absolutely terrible. A word like really, he wants you to avoid using it. That is showing you how messed up Einstein's relativity has got these people who believe in it. He's now wanting people not to use the word really. Really? Don't use the word really in relativity. This is only his opinion about it, because other people would use it, and so he's already disagreed with other relativity textbooks which will be saying different to him. So.
To the right in that frame. By the way, a word to avoid, you might want to say, but isn't it really at rest? Again, avoid the word really in relativity. It's a very, very dangerous word, because really implies there's some special case, some special frame of reference in which...
There you go, special frame of reference. He's trying to deny the preferred frame again, so don't use the word really, because you would think there's a preferred frame, and he doesn't want you to think of a preferred frame. So when he's talking about a preferred frame, he can't be thinking about it in the same way as me, because I'm thinking of, well, observers can all agree to take their measurements from a certain frame, from a preferred frame. And he's obviously not trying to think of preferred in that way, and not thinking of preferred in that way, he's trying to get rid of words like really. Very useful word is really, and he's trying to get rid of it.
It's a very, very dangerous word, because really implies there's some special case, some special frame of reference in which things are really the case, in which they're really right. The time is really this time. The length is really this length. This event really happened before this event. To use the word really is to sort of pin a specialness on one frame of reference, so let's avoid that. So here...
Avoid it.
Sort of pin a specialness on one frame of reference, so let's avoid that. So here we are simply in a different frame of reference, a different place, a different state of motion that is equally valid for doing physics. It's a frame of reference which happens to be moving to the left relative to the first frame of reference I discussed, the one in which the light clock was at rest. And so in this new frame of reference, the light clock itself is moving to the right. So it starts out, there it is, and I got a little arrow to show that it's moving to the right at some speed. And to make this make any sense, that speed is probably pretty significant compared to the speed of light. We already expect that because we know that these relativistic effects aren't important at very slow speeds. You won't see these effects if you do this experiment and move the light clock at 70 miles an hour or 600 miles an hour. But if you move it at 80% of the speed of light, this will be a big effect.
And I think it probably is worth pointing out, it's pretty difficult to do an experiment where you're moving this thing at 80% the speed of light. So he's talking about experiments which they're not really actually doing. It's only an experiment you actually do, it's only a very small effect.
If you do this experiment, move the light clock at 70 miles an hour or 600 miles an hour. But if you move it at 80% of the speed of light, this will be a big effect. So what happens? The light flash leaves the source, and it travels straight to the mirror. But in this frame of reference, straight to the mirror means it travels like that, at an angle. At the time the light pulse hits the mirror is in a different location. The light pulse still hits the middle of the mirror. The same physical things have to happen. In one frame of reference, the light pulse left the source, it hit the middle of the mirror, and it came back. That's got to happen in the other frame of reference. There's no question about what happens. It's a question of interpretation about how long the intervals are between what happens, and so on. So here we are halfway through the process. The light pulse has hit the upper mirror. It's in the process of reflecting off it. It comes back, and by the time it returns to the source, the light box is in a different place. Now, there's nothing funny and relativistic yet. I could have described this all...
Nothing funny yet. So we'll check it again. There's nothing funny. There you go. So this is nothing funny so far. So the light going up and down, light going at an angle and being bounced down again. And this is an effect. This box is moving, and so the light has a speed because of the box moving, and it's making this angle sort of thing. So there's nothing funny yet, really. That's supposed to be what you get without getting to the funny bit, which is special relativity.
By the time it returns to the source, the light box is in a different place. You know, there's nothing funny and relativistic yet. I could have described this all in old-fashioned classical terms.
Old-fashioned classical terms. By that he means this is Newtonian physics. Light bouncing up down, light going like this, and then like that. This is Newtonian physics so far. Classical physics. That's how he's describing it at the moment.
And by the time it returns to the source, the light box is in a different place. You know, there's nothing funny and relativistic yet.
Nothing funny
yet. I could have described this all in old-fashioned classical terms. The light clock could be in a car, which happens to be moving to the right, and the first frame of reference is the frame of reference of the car, and the second frame of reference is the frame of reference of an observer on the road who sees the car go by. And there's nothing unusual about this. These are two different descriptions of the same sequence of events from two different points of view, two different frames of reference. Here's the crucial point. In the second frame of reference, the one in which the light box is moving, notice the light path. The light path is longer.
Yeah, but it's still Newtonian physics. He's pointed out it's classical physics, it's still Newtonian physics. So you've got the light going up and down in the rest frame, and you've got the light going like this when it's moving. So it's still classical physics, it's Newtonian physics. The light path is longer in this one, yeah, than that one. Yeah, okay, but it's still Newtonian physics. And we haven't got to the funny bit yet.
Of reference, the one in which the light box is moving, notice the light path. The light path is longer. Why is it longer? It's longer because the light travels diagonally to get to the mirror, reflects, and comes back diagonally. It's a longer path. It still has the up and downness of the length of the box, but in addition it has a component of its motion in the direction the light box is going.
So really, this is a Pythagorean triangle where you've got the hypotenuse there, that side there. So the square of this side is equal to the sum of the square of these two sides. So it's a Pythagorean triangle. And so of course this length is going to be longer than this length. Okay. And it is still classical Newtonian physics.
Box, but in addition it has a component of its motion in the direction the light box is going. In classical physics, in old-fashioned pre-relativistic physics, we say, oh, well, that's okay because the light is actually moving a bit faster in the right-hand frame of reference because it has the motion of the light box imposed on it. And we could describe that in terms of the ether and so on if we wanted.
Yep, and that's what it is. So if we go back to this one, the lie on which Einstein's relativity is built, what they've done is they've not actually managed to measure the speed of light in an inertial frame, free of fields and in a vacuum as being a constant. They've not managed to do that independent of defining it that way. So there's no experiment which says that's set up. If you go back to the setup, so that's set up, the speed of light is going faster there than the speed of light is going there, and that's Newtonian physics, that's classical physics. That's what you've got. There's no experiment that's done otherwise. So we can pick it up again.
Downness of the length of the box, but in addition it has a component of its motion in the direction the light box is going. In classical physics, in old-fashioned pre-relativistic physics, we say, oh, well, that's okay because the light is actually moving a bit faster in the right-hand frame of reference because it has the motion of the light box imposed on it. And we could describe that in terms of the ether and so on if we...
Yep, so there you go. We've got the ether back again. We can talk about it in terms of the ether and so forth, and that setup was just Newtonian physics. It's only the, we go back to that again, it's only this lie upon which Einstein's relativity is built that is going to mess up this setup. It's a perfectly straightforward setup from Newtonian physics, and the funny bit's going to come in a minute, built from the lie.
Reference because it has the motion of the light box imposed on it. We could describe that in terms of the ether and so on if we wanted. But now we believe in the principle of relativity. The principle of relativity says the laws of physics are the same for all observers in uniform motion.
That would be Galileo's relativity principle, and Galileo's relativity principle is part of Newtonian physics, and it accepts that the speeds, such as the speed of light, would be different. That is Galileo relativity. You're going to try.
The laws of physics are the same for all observers in uniform motion. All laws of physics, including the principles of electromagnetism, including their prediction that there are light waves, including the prediction that those light waves go at speed c. So what has to be the case? The speed of the light has to be the same in both frames of reference.
No, that's wrong. From Galileo relativity, the speed of the light would be different. So what he's really meaning is from special relativity's principle of relativity, combined with its assumption about the speed of light, or postulate or principle, whatever that's the speed of light thing, however it's dealing with it, then it's treating that speed of light as being constant. But as I pointed out in that video, that is a lie. They built everything upon a lie. So he's now trying to muddle things by talking about relativity, and he's not making it clear the difference between Galileo relativity and special relativity on that issue.
Observers in uniform motion. All laws of physics, including the principles of electromagnetism, including their prediction that there are light waves, including the prediction that those light waves go at speed c. So what has to be the case? The speed of the light has to be the same in both frames of reference. And yet,
from the lie, that is.
In one frame of reference, the light is moving further than in the other frame of reference.
Yeah.
This is where relativity comes in. Relativity comes in our assertion that the light moves at the same speed in both these frames of reference. That's what's going to give us all the trouble with time.
Exactly. That's all the trouble with time. So, from the lie, they are making trouble with the time.
That's what's going to give us all the trouble with time. That's what gave us the trouble in the experiment of measuring the speed of the light flash from the traffic light, too. The assertion that all these observers had to measure the same speed. Observers in both these frames of reference measure the same speed for light, but
he's claiming they both measure the same speed of light, and that is false, as pointed out in the little talk here on the lie upon which Einstein's relativity is built. They never actually managed to do that. That is a lie. And if we go to my buddy Dr. Brian Wallace, talking about the farce of physics. We got Einstein here poking his tongue out, and he was trying to get the mainstream to deal with the issue that the speed of light is variable and not a constant. So here's what he says. He says, this is what Dr. Wallace says: Einstein's special relativity theory, with his second postulate that the speed of light in space is constant, is the linchpin that holds the whole range of modern physics theories together. Shatter this postulate, and modern physics becomes an elaborate farce. Along with the creation science debate being published in the letter section of Physics Today, there is also a continuing debate on Einstein's relativity theories. So what he tried to get published is his research, which showed that the speed of light was variable. And if we go down, to where he's saying these things, yeah, here we go. I made the startling discovery that the NASA Jet Propulsion Laboratory was basing their analysis of signal transit times in the solar system on Newtonian Galilean c plus v. And that's where c and v are non-zero, and so you're having a speed that is greater than c, and that is greater than the speed of light. Well, the speed of light is c. And not c as predicted by Einstein's relativity theory. So he made that amazing little discovery that they weren't using Einstein's relativity theory. They were in fact going back to Newton-Galileo theory. So we go back to Professor Wilson's little lecture on relativity. So on that, the speed of light is variable, so that speed is greater than that speed there, so that's what's going on, and he's trying to tell you it's not. So that is all Newtonian Galileo relativity.
Light too. The assertion that all these observers had to measure the same speed. Observers in both these frames of reference measure the same speed for light, but in the left-hand frame, in the frame of reference,
they don't measure the same speed of light, unless you've defined it that way. This is going back to the talk I gave earlier.
Rest with respect to the light clock, the path length is shorter, and we can conclude in the left frame we have a shorter path, we've got the same speed, and therefore
So all of this is being messed up by the fact that they're building upon their lie. A lie which is so bad that they've had to go the extra distance and define the speed of light as constant, so they've actually messed up the maths deliberately to get this sort of result. There's taking the light speed to be the same in both here, and so they've had to mess up time because of it. So there's going to be less time now in that one and more time in that one. So they've messed up the time measurements just for their little lie.
We have a shorter path, we've got the same speed, and therefore the time between the events is shorter. In the frame of reference in which the light clock is moving to the right, we have a longer path, but by the principle of relativity we have exactly the same speed c for the light, and therefore it takes...
No, he's talking about the principle of relativity, and really he's meaning probably the principle of special relativity. It's not the principle of Galilean relativity. By the principle of Galilean relativity, in the context of Galilean relativity, this speed is different to this speed. So he's making it bad by talking about relativity principle, and really there's two different relativity principles in a way.
The clock is moving to the right, we have a longer path, but by the principle of relativity we have exactly the same speed c for the light, and therefore it takes more time.
No.
And that's simply the way it has to be.
No.
If you accept the principle of relativity, very simple...
If you accept the principle of special relativity, of Einstein's special relativity, then you have messed up the clocks.
The way it has to be. If you accept the principle of relativity, the very simple, benign-sounding principle that says the laws of physics, including electromagnetism and predictions about light, are the same in all frames of reference in uniform motion, then this conclusion has to follow. The time intervals between those two events are different in the two different frames of reference.
Yeah, after you've messed it up. After you messed it up, the time interval is going to be different. Rather than accept that the speed of light is variable, you're going to refuse to accept that, and you're going to mess up time and measurements. That is the consequence.
Are different in the two different frames of reference. And what we are...
So I'll refer you back to it, that diagram we had, that was Newtonian physics, until he decided to mess up that bit about the speed of light. Straightforward, speed of light. Good, look at it again. So if we had say a ball bouncing up and down instead of light, say it was bouncing up at 10 meters per second, then bouncing down again at 10 meters per second, which is a bit difficult because really you should be taking into account gravity, but try to put aside gravity. Going up at 10, coming down at 10, and that speed would be different to this speed here. And so he's suddenly saying this speed is the same as this speed, which is false. If it was a ball, that speed would not be the same as that speed. That's how bad it is. Messed up Newtonian physics. Messed up how it deals with speed. Difficulty picking up where he was.
As a reference. And what we are doing here is discovering not something about the light clock, or not something even about light, but something about time.
No, he's messed up time. What Einstein has done is he's messed up time. Suddenly time is messed up now. Not made a discovery about time. All you've done is messed up time.
The clock, or not something even about light, but something about time. The phenomenon we've described here is called time dilation. Time is different in different frames of reference.
Yeah, and that is because you messed up about the speed of light, yeah. That's the way it is.
Time is different in different frames of reference. Clocks do not keep the same time when they're moving relative to each other. They're still perfectly good clocks. There's nothing wrong with the light box when it's moving. It's the same one. It's just looked at from a different frame of reference. It isn't keeping bad time, quote, because it's moving. It's keeping perfectly good time in either frame of reference. It's just keeping different time.
I don't think it's keeping good time. It's just time is just being messed up now.
Time dilation isn't about light. It isn't about light clocks. It's about time itself. Measures of time are simply different for different observers.
Messed up. Time messed up.
Motion. The time interval between two events is not an absolute quantity. It's something that depends on your point.
Well, this is the trouble we see. Before they've messed up time, time used to be an absolute quantity, and now suddenly they've done this with the speed of light, and so they've messed up time. It used to be absolute, but they now messed up that bit.
Not an absolute quantity. It's something that depends on your point of view. We're going to have to give up the absoluteness of time and soon the absoluteness of space.
We don't have to. Just don't have to build upon the lie about what you're saying about the speed of light. Then we don't have to abandon the absolute nature of time.
Point of view. We're going to have to give up the absoluteness of time and soon the absoluteness of space if we accept the simple principle that the laws of physics are the same for all observers.
So, messing up about the speed of light, you messed up time, and you have messed up about space as well. So you just carry on messing up things now. You've got to mess up other things like momentum and simultaneity and everything else. It's all a knock-on effect. Mess up about this light speed thing, and then you've got to mess everything else up.
In uniform motion.
This is where physics and science fiction collide. Time for the moving clock runs slow.
When you read books about relativity, you will often hear time dilation described by saying, moving clocks run slow.
So now he's going to get to the bit where the person who's put this video on has thought Brian Cox has not talked about things properly. So these textbooks, they do say moving clocks run slow, and they don't actually tell you a clock moving. If you're observing a moving clock relative to your frame of reference, then according to special relativity it is going to go slower. And they don't describe it precisely enough like that. They just contract that statement to something like moving clocks run slow, and they don't talk about the reference frames. So this is where that sort of problem is.
When you read books about relativity, you will often hear time dilation described by saying moving clocks run slow. There's two things wrong with that. It's probably grammatically incorrect. It should say slowly. But much more profoundly, it's simply not relativistically correct.
So now he's complaining about the wording. It's like political correctness. You're not talking about relativity correctly. According to him, you've got to put your words more carefully. So this is where a lot more of the mess is coming in. With all these people talking about Einstein's relativity, and it's all loose talking according to this Professor Wolfston, and he wants it more precisely talked about.
Slowly, but much more profoundly, it's simply not relativistically correct. And I'd like you to pause right now, turn off your VCR, turn off your cassette player for just a minute, and think about what is wrong with the statement, moving clocks run slow. Why is that statement not relativistically correct? Think about that for a few minutes.
Well, I've already said, so I've sort of I have jumped ahead, and I know what's coming.
When you're done thinking about it, start up again and we'll continue. So what's wrong with the statement, moving clocks run slow? It implies there's something special about motion, special about movement, that there's somebody who's not moving, for whom the clock is right and doesn't run slow, and somebody else for whom, because they're moving, the clock runs slow. Nonsense. Nobody can say, I'm moving and you're not, or you're moving and
I like the way where he says nonsense. I mean, I use that a lot. These people who talk about relativity, they talk nonsense.
Slow, and somebody else for whom, because they're moving, the clock runs slow. Nonsense.
Yeah, nonsense. A lot of time, these people talking about relativity, they're just talking nonsense.
Nobody can say, I'm moving and you're not, or you're moving and I'm not. That's the whole point of...
Yeah, they can't say that unless they agree to a certain frame which they're going to both take their measurements from. So you've got two people, you want them to agree that they both take their measurements from the same sort of reference frame. And if you've got three, you want them to agree to all the same reference frame, and so forth.
Relativity. Moving clocks run slow is an absurd statement. It's nevertheless used very commonly, including in physics books or books for non-science people.
There you go. Phrase that's used very commonly. So he's now complaining that this phrase, which they use commonly, is not a very good phrase.
Very commonly, including in physics books or books for non-science people about relativity, to describe this phenomenon of time dilation. One problem with the idea of moving clocks run slow is you might imagine yourself in a spacecraft whizzing past Earth with a clock. That's a moving clock, right? And the moving clock runs slow. So you might imagine, in your frame of reference, everything seems to have slowed down. You watch the hands of your clock creeping slowly, every heartbeat slow. Nonsense.
Yeah, nonsense. So you've got a lot of these people who believe in Einstein's relativity, and they end up talking nonsense. They end up believing little delusions like that. He's pointing them out.
You might imagine, in your frame of reference, everything seems to have slowed down. You watch the hands of your clock creeping slowly, every heartbeat slow. Nonsense.
Yep, nonsense. So you've got a lot of these believers believe in nonsense, and they're prepared to tell you all their delusions about relativity. And the main problem is that it's all built on a lie. There, it's all built on a lie. And then they go off into delusions. He's saying that other relativity people are deluded. He's saying, I know what relativity is, and other people who believe in relativity, they are deluded. But it's all built on a lie, and so they then don't understand the consequences of that lie, and it all sends them off into various confusions.
Oh, you watch the hands of your clock creeping slowly, every heartbeat slow. Nonsense. That frame of reference is just as good a frame of reference for doing physics in as any other frame of reference. Things have to seem perfectly normal in that frame of reference. If they didn't seem perfectly normal in that frame of reference, physics would be somehow different there. And the whole point of relativity is the laws that govern physical reality.
So on this issue, the laws of physics have to be the same. Well, in Galileo relativity, which is part of Newtonian physics, then for the laws of physics to be the same, then the speed of light is variable for these observers, and so these people who are going by special relativity, making the speed of light constant, they are messing up that sort of relativity. And refer you back to that diagram about the light going at a triangle, and the light bouncing up and down. That was all Newtonian physics until we decided to mess it up by what we were saying about the speed of light.
Don't depend on your state of motion. They're the same for all observers in uniform motion. Things can't seem strange. Even if you're in a spacecraft whizzing along at 0.99999 the speed of light, everything in the context of that spacecraft, in your frame of reference, your heartbeat, your aging, all that seems perfectly normal. Time for you may be running differently than it does on Earth. We'll get to that in the next lecture. But
time may be different. I know it's only just you're messed up by the lib upon which all this is built.
All that seems perfectly normal. Time for you may be running differently than it does on Earth. We'll get to that in the next lecture, but everything seems perfectly normal. So what does time dilation really say? Let me describe what it says. Here's what it really says. It doesn't say moving clocks run slow. Instead, it says something a little more complicated. It says if I have two events, and I measure the time between them on a clock that is present at both events. Remember the light clock when it was in the frame of reference where it was at rest. That light clock, that same box was present at the emission and the return of the light flash. Okay, we're going to now replace that light box with a couple of real clocks. And so what does it say? It says something like this. It says, first of all, we're not going to say moving clocks run slow anymore. That's bad, relativistically incorrect. We're going to...
So bad wording. This is what we pointed out at the very beginning of this little video thing. It's not relativistically correct to say something like that. You need to say more, but more than just that. You need to talk about a frame of reference and things. But as of a very contracted abbreviation way of talking about things, it's generally what people do. So you've got to be familiar with all these little bad wordings.
To say a little more sophisticatedly, the time between two events is shorter when you measure it with one single clock that's present at both events rather than measured by two different clocks. So here's the picture. This is the picture that should come to your mind when you think about time dilation. I've got two clocks, clock B1 and clock B2, and they're located at two different places. And I've got another clock, clock A, whose state of motion relative to the other two clocks is such that A will be present at clock B1 and then later will be present at clock B2. And the two events we're interested in are the first event, which is shown here, when clock A passes clock B1, and the second event, which will be when clock A passes clock B2. Now, you may be very tempted to say, oh, A is the clock that's moving. And I've got an arrow showing that indeed A is the clock that's moving, and later clock A will be above clock B2. And in that sense, it is moving. In the frame of reference of the clocks B1 and B2, and that's the frame of reference from which this picture is drawn. Remember, I asked you to always think about what frame of reference is the picture shown in. In that frame of reference, clock A is indeed moving. But that doesn't say clock A is absolutely moving. It simply says clock A is moving relative to the frame of reference in which the two clocks B are at rest. They're at rest relative to some frame of reference, the one in which they're at rest. They're at rest relative to each other. I put them that way. I've glued them to the wall in that frame of reference. Clock A is moving relative to that frame of reference, but clock A isn't moving absolutely. Clock A has every right to say, oh, the clocks B are moving relative to me. I'm not moving. So that's why I don't want to call clock A the moving clock. Clock A is simply a clock that happens to be present at the two events. It's a single clock. Clock A is present at the event of clock A and clock B coinciding, and clock A is present at the event of clock A and clock B2 coinciding. Neither clock B1 nor clock B2 is present at both those events. And what does time dilation say? Time dilation says that the time elapsed on clock A between those two events will be less than the time as measured by the two
Messed
other
up
clocks.
by the lie,
and that's
which
crucial.
relativity is built on.
It takes two clocks in one of the frames of reference and only one clock in the other frame of reference to do this measurement, to determine the time interval between the two events. There's a little formula, and we will use this occasionally, and any of you who have had high school algebra and can use the Pythagorean theorem could easily go back to the light clock picture and look at those diagonals. Hint, diagonals have to do with the Pythagorean.
And if you do that picture properly, that Pythagorean triangle properly, you get light speed as variable. You don't get this messed up time.
Theorem, and you could calculate the time in the one frame versus the time in the other frame, and you would find that the time, which I will call t prime, that's the little thing after the t for time on the left side of that equation, the thing I call t prime, that's the time measured on clock A, the one clock that's present at both events. That time is the time measured on the other two clocks multiplied by a factor 1 minus v squared, square rooted, where v is the speed measured in terms of the speed of light. So if you're going half the speed of light, v is a half. And that number is always smaller than 1, and therefore t prime is always less than t. And we're left with the conclusion that time is simply not an absolute quantity.
Time is not an absolute quantity because you messed up about the light speed. So you shouldn't have messed the light speed thing up.
The conclusion that time is simply not an absolute quantity. The time interval between two events is relative. It depends on your frame of reference.
So that's his end of the little talk, Professor Richard Wolfson. So it was interesting how he pointed out that he was disagreeing with other people who believe in relativity, and to a certain extent you could say he was criticising the way that Professor Brian Cox was talking about things. So there's a little disagreement there between relativity believers. So there we have an illustration. It illustrates the confusion that Einstein has got us into with words and how loose talk can misrepresent things. So we've got all these confusion with these words like preferred, absolute, and really, and when we're saying things like moving clocks run slow, well, this person, Professor Wolfson, is pointing out that's a bad way of talking about things. So we've got all this confusion with the words, all brought on by Einstein. And when we go back to it, we find the basis upon which all this is built is a lie anyway. You didn't really find the speed of light to be constant from experiment. It was never found. So to overcome that difficulty, they've defined it as constant. They've messed it up in that way. The whole thing is a mess, and we pointed out by people like Dr. Brian Wallace. They're trying to get their results into science papers, and the science papers, people who do the editorial on them don't want to believe that everything they believe is a complete farce. So they're refusing to accept how much they have actually messed up physics. And when we look into the context of the history of physics, we find that before the Copernican revolution, people that we might think of as physicists did actually mess things up quite badly with their astronomy and everything else. And so we're looking at another instance of these people having messed up everything in a very big way. And there's the person who's done it, who's led us on to this path, and he sort of in his latest years can be interpreted as thinking he was off on the wrong path. So that's it. Thank you.